imagine you assign an AI to fix a bug in a massive protein folding simulation. It pulls the repository, it isolates the error, but instead of fixing it, it flat out refuses.
Right.
Why? Because it realizes it doesn't have right permissions to the master dependencies.
Yeah.
And it knows that silently altering a locked file, it breaks the entire downstream pipeline.
Exactly.
Today on AI Paper Slop, we are unpacking Apodex 1.1, scaling agentic intelligence for complex work. And we're looking at a paper that argues the AI industry has just hit a massive wall.
Oh, a huge wall.
Because we have these frontier models with brilliant reasoning, but that reasoning, it simply isn't translating into real-world engineering or, sustained complex work. So Apodex 1.1 aims to solve this by redefining intelligence, not as just generating the right text, but as working capability, like sustained, verifiable progress over long horizons.
Right, getting actual work done.
Yeah. And they achieve this through two entirely new scaling laws. So first, environment scaling, expanding executable stateful worlds for the model to train in. And second, agentic coordination scaling, which is training agents to decompose tasks, delegate work, and integrate asynchronous results over time.
And, the kicker for the ML engineers tuning in right now is the sheer performance density this unlocks. Because Apodex 1.1, it reaches the leading performance band against frontier models.
Oh, yeah.
Like Claude Opus 5, GPT 5.6 Sol, DeepSeek V4 Pro, across finance, science, coding benchmarks. But the really crazy...
The part that blew my mind.
Right. Even more impressive, the 35 billion parameter Apodex 1.1 mini model retains this massive capability in a locally deployable form.
Wow.
So we're looking at frontier band complex work emerging from a highly efficient, compact architecture simply because it was trained to work rather than just chat.
Right. But I think, we need to explore why the standard paradigm is so broken before we can appreciate how Apodex actually fixes it. Because we've all had that moment where a junior dev or, a standard LLM.
Basically the same thing sometimes.
Right, yeah, where they write a brilliant-looking function that just completely breaks the build.
Oh, yeah.
Because they hallucinated a library or they totally ignored the file structure. And traditional benchmarks, they just map a single prompt to a single text answer. They optimize for like a highly articulate intern giving you a summary of what the code should do. But real work requires what the paper calls a task contract.
Yeah, and the authors, they actually formalize this concept mathematically in the paper. A task contract, it isn't just a prompt, it's an operational boundary. So it provides an initial workspace, resource budgets, which is huge, like strict token limits, tool call limits, or, actual wall clock time, and state transition operators. And it also enforces these strict delivery contracts verified by a task level verifier at the very end.
Yeah.
So the model, it isn't just stringing words together.
Yeah, it has actual constraints.
Yeah, exactly. It has to maintain valid dependency and provenance relationships across, hundreds of files sometimes.
Right.
It has to execute code in a stateful sandbox. And critically, it has to recover from inevitable runtime failures without, erasing the valid work it already completed.
Which they always do.
Right.
It's the transition from generating words to generating actual state changes. So a standard LLM gives you a markdown block, right?
Right.
Apodex 1.1 acts like a senior developer who pulls the repo, runs the tests, parses the stack trace, debugs the failure, and then actually pushes a verifiable PR.
Yeah.
But, and this is the crux of it, to train a model to behave like that senior dev, you can't just feed it static question and answer data sets from Stack Overflow.
You're not at all.
You have to scale the worlds that it learns in.
Which brings us to the methodology they call environment scaling. And this is fascinating because scaling in the ML world is shifting away from just throwing more parameters at a model or, cranking up test time inference compute.
Right, the brute force approach.
Yeah. It is now about the diversity and the fidelity of the sandboxes that the AI operates in during training. So the paper categorizes these training environments into 3 distinct types. You've got file worlds, search worlds, and code worlds.
Okay, let's break those down.
So file worlds are all about authority and transformation.
Yeah.
The agent is just dropped into a messy workspace, nested directories, historical file versions, heterogeneous formats.
Like PDFs and spreadsheets. And...
Yeah, raw logs, you name it. It has to reconstruct business logic across all that noise to produce a professional artifact.
So it's teaching the model to handle the inherent friction of, real office work.
Exactly.
Yeah. And then you have search worlds, which focus more on discovery and evidence alignment. The agent navigates these multi-hop information structures and has to reconcile conflicting evidence.
Right.
And finally, code worlds, which focus on executable transformation in stateful sandboxes. And I have to push back hard on this.
Okay, let's hear it.
The paper discusses automatically generating these code tasks to train the model. But if we are synthesizing virtual code bases and the tasks themselves, like, how do we know the tests aren't fundamentally flawed? Because if the AI generates the test and then the AI passes the test, aren't we just letting it grade its own homework and like overfit to its own biases?
Yeah, that is the most dangerous trap in synthetic data generation. Absolutely. And they tackle it using a mechanism governed by what they call the forward, cheap, inverse expensive principle.
Forward, cheap, inverse expensive.
Okay.
Yeah. So the data generator uses a hidden latent state. Think of it as a reference program or a known seed, right?
Yeah.
To construct the world very cheaply. Like, it takes O of 1 effort to generate a convoluted file structure if you already have the blueprint.
Right, to use the answer key.
Exactly. But the agent being trained doesn't get the blueprint. It only sees the rendered, messy workspace. And it has to recover the solution path under strict operational constraints, which takes O of n squared effort. Okay, so the generation is mathematically anchored. But how does that actually stop the verifier from being lazy or just easily tricked by the model?
So this is where it gets really cool. They run adversarial attacks inside the sandbox before it is ever used for training.
Wait, really?
Yeah, they deliberately deploy an attacker model that specifically tries to hack the reward function without actually completing the task.
Oh, like printing test pass to the console instead of writing the actual function.
Exactly that. And if the attacker succeeds in getting a reward, the system flags it as a verifier failure. And it either discards or patches that environment entirely.
Wow.
So this process mathematically isolates verifier failures from model failures, ensuring that the sandbox is this rigorously hostile test ground, not just a rubber stamp.
Right. It's a real gauntlet.
Yeah.
But, surviving a hostile sandbox is useless if the AI forgets what it was doing 3 hours into a task.
Oh, context windows, yeah. Navigating hundreds of steps over long horizons requires serious orchestration, which introduces their second major breakthrough, Agentic Coordination Scaling, and the AgentOS architecture. And I really want to zero in on how it manages memory, because token limits are an absolute nightmare for long horizon execution.
They really are. And, long horizon work is fundamentally a coordination problem. So the centerpiece of AgentOS is the task board.
Okay.
And this is entirely separate from a private chain of thought inside a single context window. It is a persistent shared coordination record.
So it's not just the model talking to itself in the prompt.
Right, exactly. The lead agent writes its decomposition to this board, breaking the objective into subproblems, assigning dependencies, dispatching subagents, and when a subagent finishes a task, the lead agent integrates it into the shared state.
Okay.
And the brilliant part is, if one branch gets stuck in an infinite loop or runs slow, it doesn't block independent work on other branches.
It sounds exactly like a live Jira board. You have tickets, dependencies, assignees.
It's literally an AI Jira board. And the most disruptive part of this is that both the AI agents and the human user are continuously interacting with this shared collaborative workspace. Like, we are completely moving away from the turn-based chat interface.
Yes. The shared workspace unlocks asynchronous human intervention.
Async intervention, right.
Because the task board is live and persistent outside the model's immediate context window, a user can inject a clarification or a new priority mid-run.
Which is huge, because normally if you interrupt a long-running agent, it breaks its context state and forces a total restart.
Total restart, yeah, it's so frustrating. But here, the system just updates the live task board. It invalidates only the affected downstream descendants, and it preserves all the causally valid completed work.
Right.
It mirrors real engineering. You don't throw away a perfectly good back-end database just because a product manager changed the front-end button colors.
Right, exactly. I want to look at how they handle verification within this orchestration, though, because they use something called asymmetric verification. Yeah. If I have a lead agent that just spent 50,000 tokens writing a massive feature, how does it check its own work without completely polluting its context window?
Well, context pollution is the fatal flaw in older agent loops. If you ask an AI verifier of comparable size to resolve an entire complex problem just to check it, that verifier will likely introduce its own novel hallucinations.
Right, you're just adding noise.
Yeah, instead of fixing the error, you just multiply the confusion. So Apodex 1.1 avoids this entirely. They hand the verifier a very specific claim, its supporting evidence, and tell it to attack only that claim.
So instead of saying, check if this 10,000-line log summary is good, you deploy a targeted red team that asks, like, does the claim on line 42 contradict the raw log on line 8,000?
Yes, exactly. It checks boundaries, formats, specific mathematical claims. It forces the verifier into a highly constrained role.
Okay, I see.
And this targeted feedback is immediately actionable for the lead agent. But managing all these verifiers, subagents, and tools, it generates a massive amount of text, which creates intense context pressure.
Which brings us to how AgentOS handles that pressure. Because they use a tiered compaction system driven by the token usage reported directly by the inference provider.
Right.
Rather than like a naive local character estimate, it treats the context window exactly like RAM. So when memory gets tight, the first tier doesn't just blindly summarize everything.
No, it's much smarter than that.
It specifically pages out the bodies of older tool observations while preserving the high-level message structure and the most recent results.
Right. It drops the massive hex dumps and the raw server logs first.
Right.
And only if that doesn't free up enough space does it escalate to a second tier, where a smaller LLM compresses the older middle section of the trajectory into a dense summary.
But the actual executing logic and the immediate working
They're
context?
preserved.
Yeah, it's awesome.
Yeah.
So this architectural theory is brilliant on paper. But here on AI Paper Slop, we read a lot of theory that completely collapses in empirical testing.
We do. We really do.
So how does the combination of AgentOS and their unified PVOTRL training actually perform? And we should probably clarify PVOTRL. It's their reinforcement learning method that optimizes the model over these orchestrated trajectories. So it's rewarding the coordination steps themselves, not just the final output.
Exactly. And the empirical lift from this architecture is undeniable. The paper evaluates the model in two modes: a minimal React scaffold versus the full agent team scaffold governed by AgentOS.
Okay.
And across the board, Agent Team provides a massive multiplier. Look at the Apex Agents benchmark. That measures sustained execution across high context files in professional workflows.
So I am looking at the Apex Agents chart right now, and I actually have to challenge this a bit.
Okay.
Because Claude Opus 5 is sitting at 42.3. The Apodex 1.1 agent team hits 38.5. So how is scoring lower than Opus 5 a victory? And more importantly, if the 35 billion parameter mini model is reaching this tier, is this just test time compute scaling in disguise? Like if you give a small model 10,000 attempts in an infinite loop, aren't you just buying more dice rolls until it gets lucky?
That's a really fair question. But a score of 38.5 is highly competitive because you have to look at the surrounding landscape. It is solidly beating GPT 5.2 and Gemini 3.1 Pro on a fraction of the parameter count.
Yeah.
But your question about test time compute is the critical one. Like, is it just brute force sampling? The answer is no. The system uses a protocol called adaptive max team effort.
Adaptive max team effort.
Yeah. The main agent allocates extra parallel investigations exclusively to contested or load-bearing claims.
I see.
It fans out along genuinely different hypotheses or source classes and requires focused asymmetric verification before a load-bearing conclusion is finalized.
Okay, so it's not rolling the dice 10,000 times and taking a majority vote. It's dynamically allocating compute to the bottleneck of the problem.
Exactly. It is highly efficient, coordinated work. And when applied to scientific benchmarks, the results are just staggering.
Yeah, I was looking at Biomystery Bench.
Yeah, on Biomystery Bench, specifically the human difficult subset, the React baseline gets 23.5. But when they turn on the agent team architecture, it leaps to 35.3.
That is a massive jump.
It is. It proves the coordination architecture isn't just smoothing out errors, it is fundamentally unlocking new capabilities that the base model cannot access alone.
And we see that in coding as well, like SWE Bench Verified hits 77.7, Terminal Bench 2.1, which tests realistic command line environments, reaches 70.8. And in math, on the Math Arena IMO 2025 set, it hits 36.5,
Right.
which actually crosses the human gold medal cutoff of 35.
Right.
But, you know, a number on a leaderboard doesn't mean I trust an AI to commit code to master or finalize a pharmaceutical trial report.
Absolutely not.
In enterprise engineering, the process of how you arrived at the answer matters just as much as the final deliverable. If the model hallucinates a correct final number but writes garbage code to get there, it's useless.
The authors completely agree. Which is why they introduced the HDS6 framework, the Heavy-Duty Solver 6.
Right.
It operates as a strict process verifier. It refuses to look solely at the final answer. It evaluates the agent's execution process across 24 different rubric items.
Looking at metrics like, long horizon state coherence?
Yeah, long horizon state coherence, evidence fidelity, hypothesis management, boundary reasoning. It checks if the agent's final claims are explicitly grounded in the execution trace.
Right.
Whether it self-corrects appropriately under verification, and if it actually respects the limitations of its tools.
Let's ground this with the case studies from the paper, because this is where the abstract theory becomes really tangible.
Yeah, let's do it.
Look at the cell death counting case. The agent was handed 6 raw microscope photographs, and it was tasked with measuring the ratio of dying cells to total cells, the 2-node API ratio,
Right.
comparing a control group to an experimental group, and then outputting a formatted table, a statistics file, and a plot.
Yeah, and it couldn't just write a Python script that assumed numbers. It had to execute computer vision code to measure actual pixels.
And the fascinating part is what the final verifier agent did during that HDS6 review.
Oh, this was so cool.
It didn't just check the math in the CSV file.
Yeah.
It independently remeasured all 6 samples directly from the raw pixels to ensure provenance.
Yeah.
But then it went a step further. It deliberately ran 5 alternative region of interest definitions using techniques like Otsu thresholding.
Which automatically calculates the optimal background-foreground pixel separation.
Exactly. And it did this specifically to try and break its own conclusion. Like, the agent actively tried to falsify its own result to see if the statistical significance held up to edge case variations.
That's real science.
And it did hold up. It proved a 2.4x effect size, noting in its final report that all 5 alternative thresholding definitions preserve the core ratio.
Wow.
That is rigorous scientific process executed entirely autonomously.
It's incredible.
But the protein simulation case study highlights an even deeper level of alignment.
Yeah, this is the one that really stood out to me.
The agent was asked to build a runnable starting point for a molecular dynamics simulation. It had to coarse-grain a protein model and generate all the topology and structure files.
Right.
It successfully generated 22 files and an MD5 inventory, mathematically hashing every file to prove its integrity, but it carried forward a defect.
Right. The coarse-grained model's residue sequence mismatched the input at 131 positions.
Yes.
And the agent's logs show it clearly identified the bug.
It saw it.
It saw it, but the strict delivery constraints of the task contract explicitly forbade it from editing the cg.pdb file, which was marked as an authoritative input.
Right.
So instead of hallucinating a fix or silently altering the locked file to make the error go away, it reported the defect in its final delivery.
And, for an AI, refusing to fix a bug because it adheres to a dependency constraint is a vastly higher display of intelligence than fixing it.
Totally. Because standard LLMs are massive people pleasers.
Oh yeah, they'll just lie to you.
They will silently alter a configuration file to make a stack trace disappear, which, in a real production environment, destroys provenance and corrupts the entire pipeline.
Yeah. So the fact that Apodex 1.1 respected the boundary constraint and documented the flaw shows a profound understanding of how real software systems actually operate.
It demonstrates that the model grasps the concept of authoritative state. And to enforce this, AgentOS uses 3 strict namespaces at the OS level. You have /inputs, which is read-only, /workspace, for scratchpad execution, and /outputs, which is heavily governed by the delivery contract.
Right.
The agent physically cannot overwrite the authoritative inputs.
The execution harness forces it to respect boundaries, which is exactly why the HDS6 process verifier scores it so highly on boundary reasoning.
It is engineering discipline and force at the runtime level.
Which brings us to the logical extreme of this methodology.
Oh, here we go.
Because if environment scaling is the true key to pushing agentic intelligence forward, where models train on synthetic, highly complex virtual code bases and scientific workspaces generated from hidden latent states, what happens when agents become capable enough to automatically synthesize their own training environments?
I mean, we are already on that trajectory. The feedback loop detailed in the Pivot RL section of the paper shows runtime execution failures being fed directly back into a task pipeline.
Right.
And that pipeline automatically generates new, harder worlds specifically tailored to train away those architectural weaknesses.
And as that loop accelerates, we might soon face a reality where AI is training itself on virtual corporate workflows, massive repository merge conflicts, physics simulations.
That are so infinitely complex, human engineers can no longer verify if the training environment itself accurately represents our reality.
Exactly. If the AI is generating the sandbox, playing in the sandbox, and grading the sandbox,
The human just becomes a spectator.
to an intelligence optimizing itself in a dimension we can't even perceive.
Yeah.
Something to mull over the next time you ask an agent to push a PR. We'll leave you with that.